So this video is going to focus on the first law of thermodynamics and energy sources that would be associated with it. We talked about this briefly about how the energy of the universe is constant, and so that's what internal energy is basically looking at. It's obviously focusing on the system versus the surroundings and talking about how you can determine the sum of the energy that's transferred in the form of heat as well as in the form of work. We don't see a lot with work with chemistry because we tend to have a constant volume, but say with a gas, measuring it with a syringe, you could have changes in volume, and then we would have to account for the work that's being done to the system or by the system. Enthalpy is what we tend to focus on when we're talking about thermodynamics because we tend to be looking at changes in heat when the pressure is remaining constant. The work term is not very applicable because we tend to have a constant volume as well in those conditions. So what this is just doing here is summarizing that as your Q value changes, as you add heat to the system or you take heat away from the system, you would see an increase in that Q value or a decrease in the Q value. And because Q directly affects delta U as well as delta H, delta U being your internal energy, delta H being your enthalpy, we see that they increase or decrease proportionally to those changes. Since work has no effect on the enthalpy term because the enthalpy is just Q, we see that that's not applicable, but we see when work is being done to the system that the delta U term would also increase because W would increase. And then work is being done by the system is losing energy, and so delta U would decrease. State functions are properties of various quantities that are truly only dependent on where you started and where you ended. The path you took to get between those does not have an effect on their properties. So delta T, the change in temperatures, we tend to look at the initial and final temperature. We don't really care about what happens in between. Same thing with delta U and same thing with delta H. However, how much energy is absorbed and how much energy is released, the work that is being done, those are terms that will depend on the path you took, as well as such as a distance, the path you took to get from point A to point B. So not every function that we talk about, not every quantity that we're trying to determine, we can determine solely based on where it started at and where it ended at. There definitely are terms where we're going to have to look at how much energy was expended or what else took place to go through that process. So these first two are going to be really straightforward. I know I'm going to have you do some problems where you have to calculate Q as well as you have to calculate work. And we'll do a couple of those in this video with the work term. The Q term is what you just did in the previous two videos where we reviewed MCP delta T and M delta H. So since delta U is just the sum of Q and W, we would add these two together. You do want to make sure you keep your signs in place. And when you add those together, we get that the delta U, the change in internal energy, increased by 41 kilojoules. So the system lost 47 kilojoules of energy, but it acquired 88 kilojoules of energy through work that was being done to the system. So the change in internal energy of that particular system increased by 41 kilojoules, which means the surroundings had to lose a net change of 41 kilojoules. Here we see that we have an endothermic change occurring because our Q term is positive, while we lost 147 kilojoules of energy because the system was doing work to the surroundings. So when we add these two quantities together, we see that this time the change in internal energy for our system decreased by 65 kilojoules. So that much energy was lost as a net difference between the energy absorbed and the work being done. So it asks in these cases, both case A and case B, where do the surroundings do work on the system? Remember that the surroundings are doing work when they are adding energy to the system. So that's when your work term was positive, and that was only seen in case A. Case B, we saw the system was doing work because the work term was negative. The system was giving off energy in the form of work. So now we're going to calculate a work term, and this is similar to what you would do in problems if I asked you to determine what the change in internal energy was. If I told you you had a mass of a substance that went through a temperature change of X degrees, and it has this specific heat value, and then if it was a gas in particular, it went through these volume changes at a constant pressure. So the volume of an ideal gas is increased from 10 to 100 mils. It occurs at 750 torr. Torr is the same as millimeters of mercury. And we want to know what the work value would be that's associated with this particular process. So work is the difference between, work is the product of pressure and the difference between volumes. We have a pressure term, 750 torr, and we have a volume. We have an initial volume of 10 and a final volume of 100. So we're going to take that pressure term, and we need to get it into atmospheres, because if you notice at the end of this question, I gave you a relationship between the unit of energy in joules. That 101.3 term might look familiar to you. That's the pressure for kPa that's equal to an atmosphere. And we see that if you have 101.3 joules, you have the same as a liter atmosphere. So if we can get our pressure into atmospheres and our volume into liters, we should be able to relate liters atmospheres to joules. So I'm going to use the fact that if 760 millimeters of mercury, aka torr, is the same as 1 atmosphere, that will get me my atmosphere component. I'm going to take the difference between the two volumes to get my volume component, because delta V is the change between the two volumes. And I want to get it to liters, so I divide it by 1,000 to turn it from milliliters to liters. So when I cancel out my units and I do my multiplication through, I want to have 2 sig-figs in my answer. And because of the negative sign that was associated at the beginning, we have negative 0.089 atmosphere liters of work that's been done by the system. Now let's see if this makes sense. When a gas's volume is increasing, the syringe in which it's placed, or whatever container is placed, has to expand as well, and that will only happen if the gas is able to do work to the surroundings, while if we see the volume decrease, that's only going to happen if the surroundings are pushing in on the gas, and at that time the work term would be increasing because the surroundings are doing work to the system. So when your volume is expanding, we would expect to see a work term that is negative because the system is having to do work to make that expansion occur. While if we see a volume decreasing, we would expect to see a positive work term because the surroundings are doing work to the system. At this point, we are in atmosphere liters. Our sign makes sense, so we're going to go ahead and convert from atmosphere liters to joules using the conversion I've given you. This is not one I expect you to know. I would always provide that for you. And so when we do the multiplication across, we see that the gas did 9 joules of work in order to allow that gas to expand. All right, and that is the end of this video. It should get you through the worksheet on first law of thermodynamics.